Everyone, my name is Gustavo. My advisor is the Professor André Mariano. Our work is entitled as Performance Analysis of Low-Cost Substrates in the Design of Printed Circuit Boards Dedicated to Radio Frequency Circuits for Internet of Things. So the main topic of our work is the impedance matching because it plays an important role in Internet of Things since it increases the efficiency of reception and transmission of electromagnetic waves, and that is made by calculating the complex conjugate of the impedance, whether it be from the source or the load, to achieve the maximum power transfer between the transceiver and the antenna, or vice versa. There are a lot of types of matching networks, and the proposed one is the p-matching network because it offers a higher quality factor. The objective of this work is to compare three different types of p-matching networks using lumped, distributed, and hybrid elements. The methodology is based on what is shown in the image. In one side we have the Bluetooth transceiver with its complex impedance, the p-matching network in the middle, and the other side with the 50 ohm antenna. Just to be clear, those are the proposed p-matching networks that are going to be compared, the lumped one, the distributed one, and the hybrid one. That is a combination of both. For the lumped elements, it was chosen to put two L networks connected by the virtual resistance in the middle, just for the purpose of calculations. After doing all the math, it is achieved the P lumped elements solution using two shunt capacitors and one series inductor. So the distributed element solution makes use of transmission lines to achieve its impedance matching. The stubs were placed 3 lambda over 8 apart, and after doing all the math, it results in L1 and L2. And here's the resulting p-matching network for the distributed elements. Since no analytical solution was found for the hybrid elements in the literature, we took the lumped elements solution and replaced the series inductor by a series transmission line that led to the G1 constant circuit of the Smith chart. And here's the result of the p-matching network using hybrid elements. All networks were simulated in advanced design system. The substrate is characterized by what is shown in the image, so it has a thickness of the substrate of 0.5 millimeters, a relative dielectric constant of 4.5, and the thickness of the copper layer is 35.56 micrometers. A reflection coefficient S11 simulation was done to evaluate and compare all the three proposed p-matching networks. The simulation was done from 1 GHz to 4 GHz. Since the frequency of operation of the transceiver and the antenna is 2.45 GHz, all those networks have a minimum in that frequency, as we can see. The lumped one shows the lowest magnitude, which is better. The hybrid one shows a similar solution of the lumped one because it uses the same shunt capacitors, and the distributed one shows a larger bandwidth. And also, to have more details to compare, the PCB layouts of each network were designed to compare mainly the costs involved and the PCB footprint. This table synthesizes all the information. The lumped solution has excellent performance, medium PCB footprint, and higher cost, while the distributed solution has decent performance, occupies a larger area, and has a lower cost. And finally, the hybrid solution has a similar response compared to the lumped one, has the lowest area, and medium cost. Through this comparative study, designers can evaluate and select the most suitable impedance matching type based on their specific requirements. Those are the references, and thank you so much.